Good morning, class. Let me start with what we had last time on the quiz problem. So here is the problem. Last time we worked on it. We define an LTI system using its system function, which is the impulse response Hn in the Z domain. We call that system response or system function. So this system function is in a rational format because it's LTI system. We got this numerator denominator, both are in the polynomial term. That's a polynomial of variable z or variable of z to the power -1. So we know conventionally we like to use z to the power -1 because it's easy for me to transfer back to the time domain. Okay, so anyways, we want to specify the radial convergence of Hz and then determine Hn doing an inverse ZTransform of the following conditions. The system is stable, the system is causal, and the system is anti-causal. So first we examine here, this is the partial fraction expansion. We end up in, this is last step. So we find out there are two poles for the system function. P1 is equal to 0.5, which makes the first term equal to 0, right? P2 is equal to 3, make the second term equal to 0 on the denominator. So those are the two poles. Now, because it's a function of z to the power -1, therefore I simply using 0.5. You can kind of copy this coefficient 0.5 and this 3. So I have on my z plane, this is imaginary part, this is z plane, real part. I got two poles. One is here, 0.5. And then there's 1, 2, 3. Another is here, 3, 0.5. Both are real poles. And we know for the radial convergence, it is a circle. The shape is a circle around the origin. So let's just plot out this circle that's around 0.5, cross 0.5, another large circle cross 3. This is over here, it's cross 3. And then we also want to plot out the unit circle, which is right here. That is the unit circle where I got 1 here. Right. So the system is stable. We said if the system is stable, that I will have to get this unit circle within the radial convergence. The reason being that only the unit circle actually make physical sense. Whenever I need to check the signal in the frequency domain, I am taking z equals to e to the power j omega, or in another word, I'm taking z absolute value equal to 1. So I'm not going to look at its amplitude. I'm only going to look at its phase, j to the power e to the power j omega. So I am travel along this unit circle in this direction. And that is my frequency from 0. This is frequency from 0 to pi over 2 to pi, 3 pi over 2, and back to 2 pi. And of course, we know because everything, this is this discrete time signal. So pi, this is the highest frequency I can have, which corresponding to fs over 2. What is fs? That's a sampling frequency, right? That's a sampling frequency. So when I get back, it's fs. This is the highest. That's an crystal rate, fs over 2, corresponding to 180 degree or pi. So I need to make sense that this unit circle will always be converging because the system is stable. So for all the frequency part, the unit circle is safe. The unit circle should be in the region of convergence. So if I'm looking at this picture, I know the region of convergence is either interior or exterior of circle. And those circles are bounded by the radius 0.5 and the radius 3, because these are the two poles. Therefore, for the first problem, the radial convergence is within those two boundaries, right? But within those two boundaries. To make sure that this unit circle is in the region of convergence. So the boundary is between 0.5 and 3. Therefore, for the first problem, the region of convergence is this, less than 3. Now, do I need to use less than equal to, or this is fine, less 0.5 less than z, absolute value less than 3? And of course, I need to use strictly less than, right? Because, you know, this point is the pole. The pole is not in the region of convergence. So when you're talking about region of convergence, you have to expurge this pole. So it should not include it. You need to use a strictly less than sign here. So this is okay. All right. So for this problem, we will see the solution is, we said I have two poles, 0.5 and 3. For the first problem, since the system is stable, its region of convergence must include a unit circle, and hence we have this inequality expression here. Then for each part, the first part, what I meant is this part here. Now, if you look at this part, I got a pole 0.5, and you have this region of convergence exterior of this pole, circle crossing that pole. Therefore, the first part, doing inverse ZTransform, I'm taking this format, which for the first part only, that's the causal format. Causal is region of convergence is exterior of a circle. Right? So you got 0.5 to the power n, un. It's very easy to remember that, because causal system, we put a step function un. 0.5, that's the root or the base of this to the power n, this term. And this root corresponding to the pole, we got a pole 0.5. So it's right here. The second term, now for this case, that's within the circle that cross point of 3, radius 3. Therefore, it's anti-causal, the second part. So we put a u, negative n subtract 1 here. And then again, 3 is the pole, that's the root. So 3 to the power n. And we are putting negative 2 here. Where does the 2 come from? 2 is coming from here. And negative sign is along with, when you're dealing with a non-causal signal, you will have a negative sign here. Therefore, the final answer is this. Well, this is non-causal. If you're putting all these together, it's non-causal because you got the second term. You got the second term. It's non-causal. The overall Hn, or the overall system, is non-causal. The second problem is if the system is causal. If the system is causal, then the region of convergence has to be exterior of anything, and it go all the way beyond to infinity. Therefore, we have to make sure that is greater than 3. It's just the entire exterior thing. So the region of convergence is z greater than 3. And remember, that's strictly greater than that. We're not going to include, it's not greater or equal to, because 3 is a pole. Region of convergence exclude that one. And then Hn can be easily calculated. So we got the first part is causal, second part is causal. So we use both parts un. Then the entire thing is unstable. Why is unstable? Well, because the unit circle now, in this case, is not in the region of convergence, right? Only the unit circle makes sense because those are the frequencies. I'm going to work a practical system along the unit circle. Now, unit circle is not in the region of convergence. So it's not a good system, it's unstable. Right? The third problem is if the system is anti-causal, so I know the entire thing is anti-causal, therefore, the region of convergence is interior of circle and including the origin. So the region of convergence z strictly less than 0.5, less than the radius defined by the first pole. And Hn can be written as this. Well, those two parts are anti-causal. So we have this step function here of n, negative n minus 1. We got negative sign here, negative sign here. Okay. And the entire thing is unstable because, again, the unit circle is not in the region of convergence. Okay. So that's the solution for this problem. So for this problem, we kind of doing an exercise. First, we trying to understand the region of convergence and the poles. Of course, by definition, pole should not be in the region of convergence. And we also, from this problem, we kind of understand that by given different region convergence, the final answer for the system HN can have different formats, can have different forms. Here, I got 3 different answers. And those answers will define non-causal system, unstable system. If it's stable, it's a non-causal system. So we need to pay special attention to the region convergence as well. The last content I'm trying to do for this chapter is called as Postzero cancellation. Postzero cancellation can occur either in the system function itself or in the product of system function Hz with ZTransform of the input signal X. So last time we kind of look at the output Hz times Xz. Last time we are using an example, say, well, the system is linear time invariant. Therefore, I have this rational form, Bz over Ac. And this input can also be put in 2 parts, numerator part Nz over Qz polynomial. So I have poles here of my system, poles here of my signal. I got 0 of my system, 0 of my signal. So let's imagine if I have a pole of AC are exactly same as the 0, which is the root of Nz, and those 2 can cancel out. So this is a 0 pole cancellation. Now, the benefit of this is not so obvious in this form. But let's say if I have a system called H1Z, and then I deliberately cascade another system, H2Z, and then work on HZ. So if F1Z, the original system, is not stable, how do you tell? Well, I got a pole outside unit circle. Suppose everything is causal now. Suppose everything is causal now. So I can talking about within the unit circle, outside unit circle. So for a causal system to be stable, the poles should be within the unit circle. But I got poles outside unit circle. What can I do? Well, I can cascade another system, H2, that has a 0 exactly at that position. Therefore, the 0 will cancel out that pole. And in the block diagram, you have input signal, you got H. So what I do is I cascade another system, H2Z. It's designed such that the 0 here is the same as the pole here, the out of bound pole, out of unit circle pole. And then we can cancel that and give us a very nice and stable system. We can do this very easily because for system, linear time invariant system, it is linear. So I can cascade, no problem. I can cascade. I can swamp the order. I can put in the middle of 2 systems. I can always do that. And in the Z domain, that's product. So product, you can change this order. I can plug another one in here, H3Z, as designed. It doesn't matter. So it's a really linear system. It's a product in Z domain. I can plug those in. And they give us the flexibility. I can always manipulate this stability of the system. I can do some pole cancellation in order to design a stable system. Okay, so that's we have for this chapter. Let me give you some examples on that. So let me give an example of the problem here, doing a ZTransform inverse ZTransform. In particular, using the partial fraction expansion. Let's say this example is I have a system or signal is written in this form. It's a rational format for C to the +1. I want to find the inverse ZTransform. I want to find inverse ZTransform. Now, first, as we said, we always want to make this system function or this function x of z as a function of z inverse of z, z to the power -1. It's just easy for me to do this inverse ZTransform. So we divide both numerator denominator by c squared. So this is second order, right? Denominator is 2 second order. So by z squared. So the numerator becomes z to the power negative 1. Denominator is 3. Subtract 4 z to the power negative 1 plus z to the power negative 2. Okay? And then conventionally, we want to make this a is 0, which is the coefficient here, 1. So that's subtract 4 over 3 c to the power negative 1 plus 1 over 3 c to the power negative 2. And then the numerator is 1 over 3 c to the power negative 1. Why do we do that? So one is usually this is indicated as hz. So if it's hz, you need to multiply this to the left of your equation, and this term corresponding to yn, current output. So I just want to make sure it's normalized. I pick up current output yn. So let's do a partial fraction expansion. Now for this denominator, it's very to observe how to factorize that. So we have that 1 subtract z to the power negative 1 times 1 subtract 1 over 3 c to the power negative 1. Factorize the denominator. It may be easy from this format, but either way, it's easy because the second order I can do this factorization. And then I can write it into two parts. Let me call this residual R1, 1 subtract z to the power negative 1, plus residual R2, 1 subtract 1 over 3, c to the power negative 1. Okay, so I got two poles, 1 and 1 over 3. I put that into two parts. I want to find the residual R1 and R2. Those are two constants. You can use the formula that we used in class. If we are dealing with a little complicated format, we will see another time some other examples. But in this case, because I only have two unknowns, R1 and R2, it's relatively easy to calculate. What I do, I just multiply this and then make this R1 times. Let me write out this. Plus R2 times 1 subtract z to the power negative 1. You know, this is the numerator that should be equal to this. Therefore, I can write out this equations for R1 to R1 plus R2 should be equal to what? Should be equal to 0. Right? And then negative 1 over 3 R1, which is here, subtract R2 equals to this coefficient right here, 1 over 3. That's the first order coefficient. So in this case, it's easy to calculate. So I'm just writing this to find R1, R2. And we find out, solving this equation, find out R1 is 1 over 2. R2 is negative 1 over 2. Okay, so for solving those two residuals, R1 and R2. Therefore, my original function, the function of z, can be written in this format. So 1 subtract z to the power negative 1, subtract 1 over 2, 1 subtract 1 over 3, c to the power negative 1. All right, so we got that. This is the final. This is the final for the partial fraction expansion. Now I need to transfer the inverse Z transfer back to the time domain. Now remember, we are lacking the definition of region of convergence. I'm not given the region of convergence. So there are multiple answers for that. We know that I got two poles. P1 is equal to 1. Right? P2 is equal to 1 over 3. It's given by those two denominators. Similarly, as we had before, so we got a 1 over 3 here. It's a 1 here. So I got a pole here, pole here. Need to discuss about this situation. So we have, this is complex Z-plane. I have those two. It's not symmetric, but this is -1 here. So for the first case, if my region of convergence is beyond the largest circle, which is 1. So the first case, region of convergence is the external of everything, of those two poles. Right? So it's from strictly greater than 1 and all the way to infinity. in this case, xn, x1n, I call it x1n equal to, it's a caudal system. It's a caudal signal. So it's a half, this is R1 here, times, well, the base is 1. Base is 1 to the power n, so I don't need to write this out. And then I write this step function, un here. Subtract 1 over 2, that is R2 here. That's the second residual. And the pole is 1 over 3, because that's to the power n. And again, that's a caudal function. So we have that. And then, of course, I have some other possibilities. Region of convergence. If region of convergence is in here, less than 1 over 3, is in this region, okay. Then what I will have is I got my x2n equals to half the first part. This is second part, anti-causal, negative n minus 1. And the first part is also, put a negative sign here, it's also anti-causal. So u negative n negative 1. Okay, so the entire thing is within this is region convergence, so within circles, and then I have an anti-causal system. The third case is region convergence is in between these two. So in between these two radius, 1 over 3, between 1 over 3 and 1, and therefore we can quickly write out this. The answer is, this is the first part is anti-causal part, and the second part is a causal part. The entire signal is anti-causal of un. Okay, so I have the answer for that. Those are the 3 possibilities. It's depending on 3 different region of convergence. Okay, so let me use Matlab example to check the answer. What I want to do is I want to use Matlab to check with ZTransform, showing the Z-plane, showing 0 in the poles, and then also showing a spectrum, showing on the unit circle what we're going to see in the frequency domain. Just get all familiar with some of Matlab code, and again, for all these Matlab code, because the program is very extensive and the software is evolving all the time. I'm not asking you to understand or to memorize every single command line, but I need to train you, have this ability, so you know some tool you can use. And a lot of those functions I don't even know, so I have to check what is the Matlab functions, the current functions for ZTransform. Now with my knowledge, basic knowledge, knowing the theory of ZTransform, I can using some of the tools very, very easily. I put a signal x1, x2, and then first I do a convolution. So here, let me just copy that, put in. Okay. So this is in the time domain. I'm doing a filtering, it's convolution. So I have 2, 3, 4, convolve 3, 4, 5, 6, co-convolve x1, x2. I got this result. And the length of this is the length of x1 plus the length of x2 subtract 1. So in this case, the length of the convolution result is 6. There is a command in Matlab, actually, we can do deconvolution. So deconvolution is written here. Let me copy this line here. Go. So deconvolution is, in this case, I'm deconvolve x1 out of x3. So it's almost like we are doing a long division, a polynomial division. If you think that x3 is a vector, those are the coefficients of a polynomial. x1, those are the coefficients of a polynomial. So we are doing a long division of 2 polynomials. In that case, x will be the quotient, and r is the residual. So in this case, x is this x2, 3, 4, 5, 6 exact. R is all zeros. I don't have that. That's all zeros. So the residual is 0 because I can do this long division perfectly. It's coming from x1 combined with x2. So we can easily show that. I'm just showing you before I'm getting to ZTransform some of the command code. I understand that you can check your answers using deconvolution as well. Okay. So let's see now for the problem I just have. Write out this again. The problem I had is xz equals to z over 3z square subtract 4z plus 1, right? This is the problem we just worked on. So if you look at this format, the polynomial of numerator, in this case, the coefficients are 0 and 1. 0 and 1. And the polynomial, 1 is because I have a 1 here. And then the polynomial of denominator is 3, -4, and 1. You may it's not maybe not that clear here, but if I am putting everything, so if I change that, the second is changing that as a function of z to the power -1. You divide z to the power 2 on both numerator and denominator. So this is what I have: 3 subtract 4 z to the power -1 plus z to the power -2, right? This is what we have conventionally. We got this format. And then it's easy to understand now. B is a function. B is a polynomial with coefficient 0 and 1. 0 is the coefficient B0, which is of z to the power 0, which we don't have here, which we don't have this term. The second term is this one here. That's the B. Okay, and A in this case is 3, -4, and a 1. Exactly here, right? So we are using this to represent this system function exactly, or this function. And then what we do is we are using a command called residual z, B and A. That is going to give me, it will do a long division. So what it will give me R, which are the residuals. Those are R1, R2, if you remember, I have in this problem. P is a vector of poles. So 1 subtract P1, 1 subtract P2. Okay, those are give me those P1, P2. Those are in the vector of P, and R is the vector of this residual R1, R2. So it's kind of doing this partial fraction for you already. It's numerically give you the answer. And then C is when you divide the polynomial. It's a quotient. It's a quotient. So in our case, we don't have that term. Now, if this is improper rational format, I'll have something here. I'll have something here. But in my case, I don't have that. It's all 0 because it's proper rational format at the very beginning. So in this case, C should be all zeros. Okay, so let me work this. I copy that. Okay, now this is what I have. And I have R is 0.5, -0.5. That's exactly what we calculate, right? It's 1/2 and -1/2. A pole is 1 and the 1/3. Those are the two poles. And the C, as we understand, C is an empty set because I don't have the quotient part. So very nice. In Matlab, it can check the partial fraction expansion for us, doing a long division, and give us all the answers here. The residual Z can work both ways. If you have all these, the residual, the pole, and the quotient part, and using the same command, you can find out the coefficients B and A's for the polynomial. For the polynomials on numerator denominator for my function X. So let me do this so you can see. I recover back B is the vector of those two coefficients where the first one is 0. The second one is 1/3. A is the coefficient of the denominator. It's 1, -4/3, and 1/3. In this case, because everything is normalized. This is everything is normalized. What you get is you got this equal to, remember we also calculated 1/3, 1 subtract 4/3, plus 1 over 3, C negative 2. You got the, so these are the coefficients. Let's say A is coefficient here, B is the coefficient here. Okay, so very nice. We can always check. We can always check this answer. Even more in MATLAB, let me continue to show you here. So if I only know the poles, I do not know the polynomial coefficients. That's okay, because in MATLAB you can generate a polynomial given its roots. Generate a polynomial given its roots. Suppose I have roots as 0.9, 0.9, negative 0.9. So those are the roots for this polynomial, and I'm putting as a coefficient for A. Therefore, these are the 3 poles, right? These are the 3 poles. And the B is 1. So numerator, that's just 1 over that. And then I check with my answer. At the same time, let me plot this out. So I'll do this. So we can see now I find out the R is the residual. So these are on the numerator, right? It's 0.5, 0.5, negative 0.5. P are the 3 poles. Sure, it comes from this polynomial. Sure, polynomial generated by those 3 poles or by 3 roots. So the poles should be exact. Negative 0.9, 0.9, 0.9. And then the quotient part, I don't have that, so it's empty. Okay, so this is when I type in C plane B comma A. I give the coefficient of those 2 polynomials, and it will show me something here. And in this case, it's I'm just using a 0 at origin and a pole at 0.9. So you can plot this out. It will very nicely draw the unit circle for you. So it's here. Okay, so you can see what I did here. This is figure 1. I plot out B is 1 or 0, actually just 1. A is 1 and negative 0.9. So what is that? Well, that will give us 1 over 1 subtract 0.9 C to the power negative 1. So this is what I have. And I have a 0. I have a 0 at the origin. I don't have a 0 in this case. It's at the origin, usually omitted. And then I have a pole at 0.9. That's what we have here, exactly. Okay, that's what we have here. So you can use a Z-plane. Very easy to show that. Now, I also want to show what if I travel along the unit circle. As I explained, when I travel along the unit circle, I'm checking with the frequency. I mentioned this again and again. Later, we will know that's exactly the bridge. I will call this a bridge between Z-transform and the Fourier transform. So Z-transform is a general case. Fourier transform is a special case. I'm not going to check with all the Z values. I'm only going to check Z value when the mole of Z is 1. So I'm only going to check on this unit circle and travel along this unit circle. That's where you get the special case of Z-transform, Fourier transform, okay, on the Fourier domain. So I also want to show the same B and A here. Now I know it's 0 here, a pole here. Let's see how it looks like in the frequency domain. Before I draw this out, I get a feeling I'm traveling along this unit circle. So if I'm here at this point, which is DC, my frequency is 0, right? This frequency here is 0, and it's close to the pole. When it's close to the pole, the value of XZ should be quite large because it's close to the pole. If you draw into the pole, then this value becomes infinity. Then I travel around. 0 is in the middle, so it doesn't affect too much. But I know when I close to DC, I got a quite large response. So let's see here. Now I am doing both of here. All right. So on the second part here, what I did is HZ is frequency Z. We showed this once before. Frequency Z is going to show me a spectrum. I also using polynomial coefficients b and a. H is the value. W is the frequency. So I plot a span W, plot W, and absolute value H. So I plot the top picture should give me the amplitude or the magnitude. The bottom picture is angle of H. So it gives me the phase of my output. So let's look at here. That's what we have. So indeed, I have something. This is the magnitude response. At 0, because I'm closing to the pole, so it gives me a large number. As I'm going further, it's just giving me a smaller number. And the bottom picture showing me this phase, but the phase is nonlinear. This is highly nonlinear. Why is that? Well, because this is infinite impulse response, IIR system, right? You got a feedback. You have something on the denominator. That's the feedback. So you will have a nonlinear system. And that showing in the phase, that's not a straight line. It's just some curve. Okay, so let's try another one. Now, if I'm going to draw the frequency spectrum of the entire from 0 to 2 pi, and then what you can write is you can write that I want a whole of the spectrum, and I'm plotting out 200 points, and I draw this. So let's see. And it's all the same here, but the only thing is I'm going to use 200 points. It's from 0 to fs, to sampling frequency, or from 0 to 2 pi. All right, but we know we don't really need that, because beyond the Nyquist rate, everything is a mirror image of itself. So you have the redundant information. That's why our original layout, we don't need a whole. We can just plot from 0 to pi. That's good enough. In other words, when you travel along the unit circle, you just go half circle from 0 to pi, and you got all the information, or everything that should be there. And then the same thing here for the phase term on the bottom picture. The phase is also, it's a mirror with the center at the pi, or fs over 2. So now let's move to something that is interesting. Let's see if I have a special case I designed here. All right, so this is my B, and this is my A. So B is this vector. Those are the coefficients. So what we have here is 1 plus 0 times c to the power negative 1 plus 0 times c to the power negative 2. How many we have? This is 1, 2, 3, 4, 5, 6, 7, 8. So we got the last one is subtract c to the power negative 8. So I don't have the middle term. So the entire thing is 1 subtract c to the power negative 8 on the numerator. And then the denominator is just 1, right? So this is my signal in the z domain. We got that. We plot the z plane with this coefficient b and a. We don't have a poles, but imply those poles are at origin. It's going to show you, but we don't really count those. Where are the zeros? Well, zeros is need to make sure that the numerator, 1 subtract z to the power negative 8, equal to 0. So z to the power 8 equal to 1. And what are the solutions for this equation? Z can be positive negative 1, right? Z can be positive negative j. Well, actually, z, it is, if you draw this on the unit circle, z can be taken this point, that's positive 1, negative 1, positive j, negative j. Z can also take at this point, which is 1 plus j divided by square root over 2. Z can also be this. Z can also be, it's positive negative 1, positive negative j. So those are the 4 points here. Right? And because z is a complex number, so solving this equation, you are going to write out this is equal to e to the power j to 2 pi times k, where k is integer. And then you find out z is equal to e to the j 2 pi k over 8, where k is an integer. So in this case, k is 0, 1, 2, 3, all the way to 7. And then you, beyond 7, you got 8, becomes your original 0. So we have those solutions for those 8 numbers. Again, because z is a complex number, so we need to think in the complex plane. All right, so let's see if this is the case from my plot. So what we have here is figure 4 first, and figure 5. Figure 4 is showing, that's a Z-plane. So indeed, it's showing me 8 poles on the origin implied. And I have 8 zeros at the unit circle. Now we care about these because when I have a real system, I really travel along the unit circle. So it affects me. I'm traveling along the unit circle. Those are the 8 zeros. So what does that give us when I check with spectrum in frequency, in a practical system in frequency? Well, that when you travel along this, you will fall to 0 when you started at DC. And then you travel along here, you got this part. This part is your frequency pi over 4. And of course, we know that you need to somehow map that out with your sampling frequency. But digitally, in the digital world, we know that's a frequency pi over 4. This is a frequency pi over 2. And when you moved here, that gives you all zeros. So that gives you this xz or hz if it's system. That gives you this value equal to 0, exactly on this point, on those 8 points, right? So I'm doing a frequency z, so that's going to show me the magnitude response and the phase. Indeed, the magnitude response is that, I have those 8 nodes. Those 8 frequency points is exactly I move to the 0. So my hz or xz becomes 0. Now, if you look at the phase, it's actually a linear phase system because it's a FIR system. I only have numerator. I do not have anything on denominator. And what you see here is because of the wrap effect. So you wrap around pi, positive and negative pi over 2, positive and negative pi over 2. So when you connect all these together, it's a straight line. Okay. And then lastly, since we play with zeros, let's also look at what about poles. So the last example I have here is that I make b equal to 1, but a is here. If you look at a, this coefficient or here, what we have here on the denominator is 1 subtract 0.9 times z to the power negative 8. Okay, so that's what we have for this function. Now, I want to make the poles strictly within unit circle. Therefore, I put a 0.9. I want to make these all 8 poles strictly within unit circle. Then doing the same thing, I plot out the z-plane. I plot out the frequency, magnitude, and the phase. So here is the picture for zero and the poles. I do have 8 poles that's close to unit circle. Remember, I put a coefficient 0.9, it's not 1. So it's not exactly on the unit circle, but it's close to the unit circle. I have exactly those 8 poles. Now, when I travel on the unit circle, I'm checking frequency. Then if I'm moving close to DC, moving close to frequency pi over 4, I should get a large number because it's close to a pole. You just simply have this h of z, this number, quite large. And then lastly, what we see here is the frequency. That's the last picture. So yes, as we designed, I want to make sure that on those 8 frequency positions, I have a very large magnitude response. I have a very large hz. So indeed, this is the case. I got those 8 spikes, very large. And you can imagine if I have the poles on unit circle, those spikes will be upward to the sky. It blew up very large. And then we check the face. This face is a nonlinear. They have some of curvature here. It's not a straight line. If you connect, it's not a straight line. Because again, this is an IIR system. I have the numerator is constant 1, but the denominator, we have some of a polynomial. We got some values of a's there. And that gives me some feedback that tells me that the system is nonlinear.